Okay, we're going to start a new unit today on classification. So in this unit, the demo is about diagnosing breast cancer. And in particular, it's about a procedure where some tissue is stained and viewed under a microscope, and an expert visually inspects the cells and translates what they see into several measurements. And those measurements are treated as features, and the target is whether the subject is cancerous or not, whether whether the tissue is benign or malignant. And so this comes from a paper from 1995, and the data set has 683 samples and 9 features, and the target, we said, is one of two things, malignant or benign. And here are the features. And the key thing I want to point out is that these are all integer features, which has some implications in how we plot the data. So let me ask, is Yang Shen here? So are these ordinal or categorical? So remember, the difference is when things are ordinal, they're ordered. So when we talk about clump thickness going from 1 to 10,
we use the A1 to that X1, not the number.
No, because I'm just measuring the thickness, right?
Oh, all right.
And the thickness is like 1 is the thinnest, 10 is the thickest.
So that's just a number.
Exactly, this is ordinal. So here we see an example. So when you see something that's discrete, that does not mean it's categorical. It can be discrete yet ordinal. And all of these features are discrete, even though, they're all ordinal, even though they're discrete. But what makes classification different from regression is that the target is what is categorical. So in this case, there's 2 categories for the target. In general, there might be 3 or more categories for the target. And we don't think of them as ordered numbers. We just think of them as different categories. And that's what makes classification, what we're studying now, different from regression, which is what we have studied until now. So integer but ordinal. And then this one is categorical. Sorry. Okay, so that's the data set. And so now this is in the demo, but we would like a way to visualize it, because visualization always helps. Us humans can pick up a lot of patterns by looking at things visually. And so because all the features are integers from 1 to 10, we cannot use our traditional scatter plot, because what would happen is all the points would sit on top of each other. And for example, if there's a bunch of points here, it would just look like 1 point, right? You can't tell how many points there are. So we did something a little different in this picture. The more points, the more samples that have a feature right there, the larger that dot is. Okay, so now you can use the dot radius as a visual assessment of how many samples had those features. And second of all, since there's 2 classes, we're going to plot all the benign samples in green and the malignant samples in red. So you can see that there's some, and this is just 2 of the 9 or so features we have. Can't visualize 9 all at once as a human, but we can look at 2 at a time. And so, like, for example, the samples that had 10 and 10 for those 2 features, there was several of them, and all of them were malignant. Whereas down here, all of these were benign. And then this one, most of them were benign, but you can see there's a malignant one in there as well. Okay, so this is just a visualization of the data. And so overall, when you look at this data and you imagine that we want to make some sort of decision rule that maps these two numbers to benign or malignant, how would you go about it? Does anybody have any guesses or any intuitions just from this picture? Yeah.
Odds increase roughly as each parameter increases.
Okay. Well, okay, we have really we have a pair of parameters. So given, let's say I give you a location on this graph and we want to determine whether, we want a predictor that says whether that location is malignant or benign. What does that kind of translate into at the end? Any guesses? Yes.
I mean, if size, if both factors are low, it's probably benign. Both factors are high, it's probably
Yeah, exactly.
malign.
And how do we make that even more concrete? Could we draw like a line, like a border, a boundary? Yeah, so maybe we would put a boundary, something like here, right? We would say if it's to the southwest of the boundary, we would classify it as benign, and if it's to the northeast, we would say it's malignant. So that's exactly right. So that's the intuition that we have, and that, as we see, is sort of exactly what we're going to talk about in this unit. And there's going to be a question about how you make that boundary. Is the boundary a line, or is it a curve? You know, or maybe the boundary is complicated. But those are the things we start thinking about now that we're talking about classification. Any questions? Okay, great. Okay, so binary classification, kind of starting at the beginning here. Just as before, we're given a set of training data pairs. This is supervised machine learning, so we have data in pairs. So the things we're using for prediction, the features, and the things we're trying to predict, the targets or the labels. The difference now is that, and by the way, we're talking about binary for now. We'll talk about more than two classes later, but first we're starting simple. So we have the targets are going to be categorical, binary. So basically, we need a way to represent them. You know, since Python works in numbers, we're going to represent them with two integers. But like in our minds, we could think on, off, A, B, malign, benign, malignant, whatever you want. And if we're going to use two integers, we can actually be quite arbitrary in the two integers we use. For a lot of the math, for a lot of our derivations, it's very convenient to use 1 and -1. So that's what we're going to focus on. But sometimes it's popular to use 0 and 1. And so we'll also talk about what happens when you do that. It's really, conceptually, it's no different, but the equations just change a little bit. Okay, so that's kind of the setup. And the applications of this are like whenever we want to classify a sample as one of two things, like are the cells cancerous or not, or maybe like is this picture showing a weed or a crop? So that's the setup. And in terms of the math, we want to design a function, h, that takes in the feature vector. In this case, I'm just thinking about like a test feature vector x, and it outputs a classification guess. And different from regression, in this case, what comes out of h has to match this target domain. So if the labels are in 1 - 1, that set, then the output of h must be also in 1 - 1. Okay, it can't be a number like 0 or 0.5, because you would say, I don't know what you're talking about. You know, either it's cancerous or not, either it's a weed or it's a crop. You're giving me something that doesn't fit that description. Okay. So obviously we would love that the y hat that our predictor generates is the truth, but we cannot, we can't guarantee that it's always going to be true. And so really what we want is that they agree as often as possible. So we would say maybe with high probability. That's what we want. And as we just described, we can think of this binary classifier as two decision regions. It's another way to think about it. So in the picture on the right, I'm showing a scatter plot where we have a bunch of training samples from one class here and a bunch of training samples from the other class here. And now I might design a classifier that I can associate with this decision boundary, where everything on this side of the boundary is going to be treated as that black class and everything over here as that white class. And so mathematically, we would say, like, we would build one region as the set of features x such that h of x equals -1. That could be maybe this. And then the other region is a set of x such that h of x equals 1. Okay, so we can think about h through its decision regions, or we can think about it as a function taking features to something in our label domain. Does that make sense? Yes.
Does like -1 versus 1 matter? It could be 1 versus 2.
Yeah, exactly. Conceptually, we could use anything. We could use 1, 2, 0, 1. In fact, this data set, for I don't know why, but it uses 2 and 4. Yeah, as long as those are different, it's fine. But for a lot of our derivations, when we use these numbers, they get a lot cleaner. So that's why we will often adopt this, just because, yeah, the equations become simpler. Yes?
So here we assume standardized data for
Um,
zero and line.
So if you're going to use some kind of regularization, it's important. So if we want to use like L2 or L1 regularization with what we do, which is something we're going to consider, then it's important. If you were running this without any regularization, it wouldn't make a difference. You would get the same, once you train it, you would get the same H. Okay. Now, it turns out, as we'll see, if you don't add any regularization, something weird can happen with the main type of classifier we'll design. And so by default, it always includes ridge regression. You can substitute lasso if you want, but by default, sklearn uses ridge. And so there you would kind of say, well, since it's going to be using ridge, I may as well standardize my features. Okay, good question. All right, any other questions? Okay, great. So now, this can be, classification is a possibly very generic and very complicated thing. So to start, we're just going to study the simplest kind of binary classification, which is what's called binary linear classification. And it's really linear in two different ways that I'll describe in a moment. But basically, we can think of this thing, linear classification, as a two-stage procedure. The first stage is that we're going to compute something called the score or the discriminant. And this is going to be a real number. And we are going to, we're going to write it like this. Z equals B plus a sum over the feature index J from 1 to D of Xj Wj. Okay, so Z is what we call well, I'll usually call it the score, but sometimes people call it the discriminant. That's the first step. And this is a real number. Okay, this is not categorical, this is a real number. So in the second step, what we do is we threshold that score, and we return for y hat 1 if z is greater or equal to 0, or in this case, -1 if z is less than 0. Okay, so it's the second stage which really gives us the outputs in the domain that we're working in. And the first stage, if you look at it, looks pretty much identical to linear regression, right? The only thing that's different here is that we've changed the notation for the prediction coefficients. Instead of beta 0, we're using B. And instead of beta 1 through beta D, we're using W1 through WD. Okay, so I didn't do this just to be confusing. It's just that most of the literature on classifiers as well as neural networks and things like this, it uses this notation, whereas most of the literature on regression uses that other notation with the betas, using the same variable for the intercept and the slope parameters. So anyway, we're kind of changing our notation, but really conceptually, this is exactly like our old y hat that we generated in linear regression. It's just that now we do this one extra stage to it. Okay, so that's, so why do they call this linear? For two reasons. So the first reason is that z is a linear function of these parameters b and wj, just like we had for linear regression. And also, z is linear, affine linear, in the features, right? So it's a linear function of b, it's a linear function of the w's, it's also a linear function of the x's. So, it's really linear in two different ways. Okay, and then we usually combine our weight coefficients into the vector boldface w. And we learn w and b from the training data. How exactly we do that will be what we talk about today. But is the setup of linear classification, binary linear classification, clear? Like what we're doing? Okay. Any questions on this? Okay, great. So let's now think about this decision boundary that this kind of classification procedure implies. So if you look at this equation, you notice that the boundary, the place where you switch between y hat as 1 and minus 1 is exactly when z equals 0. And so when z equals 0, that's the decision boundary, right? Decision boundary is equal 0. But also we have this equation for z above. We can think of this as b plus x transpose w. So we can write it like this. And so what that means is when we want to describe mathematically this hyperplane, it's going to be the set of x such that this is satisfied, such that this equals 0. This is the set of x that gives us this hyperplane. So I should clarify. So these pictures are like looking at x1 and x2 in the feature space. So there's an infinite number of points along this line that are in this set here. Okay, so when you look at these decision boundaries, if we look in 2 dimensions, like here, it's going to be a line. What is it if we would look at this in 3 dimensions? Let me ask, is Elena Sun here? Okay, what about Hannah Wang? Okay, what about Emily Weigel? Yeah, so imagine that I had another dimension, coming out here. How would a linear boundary look like, do you think? A plane, exactly, a 2-dimensional plane. And in 4 dimensions, it would be a 3-dimensional plane and so on. And we can't really visualize things anymore, but mathematically, the name we use for that is a hyperplane. It's basically a plane in any finite dimensional space. It could be a line here in 2 dimensions, it could be a plane in 3 and so on, but it's generally called a hyperplane. Okay. Okay, great. Any questions so far? Okay, so that's what's special about these linear classifiers is that they have linear boundaries. And so like this, you could not do this with a linear classifier, at least directly. Okay. So you might then ask, when does linear classification work well? When does it fail? When should I use it? And so on. And it tends to perform well when the training data are what we call linearly separable, or when they're nearly linearly separable. And by linearly separable, we mean that there is some hyperplane that perfectly separates the training data into the two classes. So here we have a picture of where the labels are from one class, and here are the training samples where the labels are for the other class. And you can see, yes, I can find a boundary, or you could say I can find a B and a W such that the boundary perfectly separates those two classes. And in fact, I can find many boundaries. This one also works. So this is how we define linear separability. Perfectly separates the training data according to the class. So coming back, like here we have linearly separable, here we don't. It's impossible to find any linear boundary that perfectly separates this data because the data overlaps there. Okay, so is the idea of linear separability pretty clear? Okay, so in practice, most real world data sets are not linearly separable. That would be too easy. But linear classification is a sort of thing that you want to use if you have something that is pretty close to linearly separable, something like this. On the other hand, if you have something crazy like this, where all the blue points are in here and the green are out here, you don't want to directly use a linear method because you can see there's no way I can really do a good job of separating that data. So, okay. Yes?
If you go back a slide,
Yeah.
what is, I guess I'm confused on the two axes, x1 and x2.
Yes.
So those are our features?
That's right. So kind of like this picture too for this data set. So we have these two biometrics, and then what we're trying to predict is cancerous or not, right? And so we have this categorical label. And so we said there, like, if I could put a decision boundary here, that would be pretty good. Like anytime the feature pair, that pair of numbers is below here, that would be a good time to predict benign. But if it's on the other side, I'd predict malignant. And so this is really the same kind of thing where you have samples in one class, samples in another class. And this boundary describes the set of X that is right on the border between blue versus red. Is that making sense? Yeah. Okay. And the linearity of the boundary is directly related to the linearity in the x's. Because z is linear in these x parameters, that's what makes the boundary linear. Okay. Good. So everybody understanding linear separability and these linear boundaries? Okay, great. So briefly, let's talk about linear versus nonlinear classification. So as I just said, most of the time in real life, the data sets are not linearly separable. And there's many ways this can happen. It could be, you could have data that is just very far from linearly separable. You could have things that are close. Maybe there's an outlier here that's preventing it. Or, something like this. This is also, I guess you could try to classify it like this, but again, you have all this overlap. And this would be linearly separable. So, okay, why are we going to focus on linear for a little while? Well, several reasons. It's easy to understand, easy to analyze. We studied feature selection, and we saw that that's another power of a linear method, in that, like, if we normalize our data and we notice that some of the W's are much larger than others, then we know for the purposes of predicting the class, those features are more important than the others, right? So there's something to be learned about the features. That could be useful in science or medicine or something like that. But also, like we saw before, we can, if we allow us to use a nonlinear feature transformation before applying our linear classifier, we can do all kinds of crazy things. So just as an example, we know that over here, if I look at the raw features, x1 and x2, there's no way I can make a good classifier based on the raw features. But what if I sort of transform my data set and I make a new feature, I'll call it x prime, which is sort of, imagine that this is the center, and it's basically the radius. So I take x1 squared plus x2 squared, I call that x prime, and now I do linear classification with the x primes. In this case, my decision boundary will look like this. It will look like some circle. So as W gets larger, that circle gets bigger. And so, so now you can see, well, if we allow ourselves to do these feature transformations before applying linear classification, we can do all kinds of stuff. And it turns out that that's exactly what happens in all the state-of-the-art classifiers, whether they're built on neural networks or transformers or whatever. They essentially do all this fancy pre-processing, nonlinear pre-processing, so that the linear classifier, which is the very last stage, works great. Okay, so this is really just linear classifier. Linear classifiers are an important building block, as well as being easy to study and facilitating feature selection. Okay, all right, any questions? Yes.
So is it ever done, so like for the lowest
Yeah.
plot labeled B here, you could consider like a subset of the data points and develop like a linear model that covers a subspace and then piece together, is that something that's ever done? I mean, you're considering smaller amounts of data.
Yeah, you might be thinking about decision trees, which we will talk about in a couple units. And a decision tree is kind of like, you can think about it as sort of a recursive procedure where you work one feature at a time, and you might say, like, based on my first feature, I'm going to sort of say, is it above or below a threshold?
Yes.
And then I'm going to look at my second feature and say, okay, now, in doing so, you kind of, right, that's decision trees. We will talk about that in, I think it's going to be unit 8 or maybe 9. Yeah, we'll definitely talk about that. Sure. Okay, great. Okay, so let's move on to how we fit the parameters. That's the main question for today. So because we noticed that this looks a lot like linear regression, right? This part is exactly like linear regression. You might say, why don't I just basically use something like this? Instead of Z, I'll just use this as my training, samples Y, and I know how to basically do least squares fitting of the B's and the W's so that my predictions are close to my training samples, right? So I could definitely do that. And let's see exactly how that works. So, this is the question. Can we just use least squares fitting? And so for RSS, essentially what we have is we can write this as the norm of the training vector Y minus the, how do I want to write this? We're going to use the A matrix, which is like the features, but it also has that first column of ones, and then we're going to stack the B vector on top of our W vector to make a vector of trainable coefficients. And so this is going to be our RSS. So we can figure out in closed form the B and the W that minimize this on the training data. And then once we have those least squares parameters, if you give me a new test vector X, what I would do is I would first compute the linear score corresponding to that X, and then I would threshold it to give you your final test prediction. Right? So I could definitely do this. But the problem is, this doesn't actually work well. Okay, is it clear what we're talking about doing before we go on? Pretty clear? Okay, so let's just look at a very simple case of if I have a single feature. So this is my single feature, and this is my training data, these dots. So I'm told that if these samples are all y equals -1, and these 4 samples are all y equals 1. And as a human, if you were given this training data, you'd say, well, this is pretty simple. It seems like I could just put a threshold in the middle there, and if my feature is to the right of that line, let's say 5, then I would guess 1, and if it's to the left, I would guess -1, right? So that's pretty simple. And actually, if you do the least squares fit, and this is all in demo, it computes a B and W that give you this z hat. So by that I mean z hat would be 1 times x, and then we have like b hat and w hat because there's only 2 coefficients here. And so now what I'm doing is I'm plotting this versus x. And so there's going to be basically like an offset, and then it's going to be a linear slope. So the slope of this is going to be whatever we learned for w hat, the fitted coefficient. And then we threshold it. So whenever z hat is greater than 0, which happens whenever x is greater than 5, we would report 1. That's this green trace. And whenever it's left of 5, we report -1. Okay, so everything works perfectly here. Seems like great. We're pretty happy with the least squares procedure. Is it kind of clear what I'm showing here in the figure? Okay, so now what we're going to do, which is kind of, you would say, is not really that difficult, but I'm going to move this point over here. Okay, so as a human, if you were given this data set, you wouldn't really change your decision rule. You'd say, well, I can still use 5. Anytime it's above 5, I should report 1. And anytime the feature is below 5, I should report -1 as a class label, right? And it's kind of like, it's almost counterintuitive that this should be a problem, because it seems like the difficult part of making decisions here are when the samples are close to 5. So as you get samples that are close to here, then it's going to be like, well, I don't know. I'm not very confident about classifying them. But if I have like a sample that's very large, like 20, a feature is very large, it seems like, well, that's should obviously be a 1, or if it's like a -20, that should obviously be a -1, right? However, what happens when we train these least squares coefficients is we actually get a w hat and a b hat and a w hat that gives us this orange line, and then the orange line basically crosses 0 whenever the data, the feature is like about maybe 7 or so. And so now this is giving us a prediction that even on the training data is making a mistake. It would actually classify this training point as -1, even though we know that the training label is 1. Okay. So what we see here is that when the features are kind of symmetric in the feature space, everything works well. But when the features are asymmetric, meaning these are kind of clustered like this and these are spread out wide, things seem to fall apart with this least squares training approach. Okay, is that clear what's happening? All right, and the problem is that this RSS idea, we just kind of like applied this without really thinking about it too much. It turns out that this is really the issue here. It's not that linear classification can't work, it's just that training it this way is not going to work whenever the data is asymmetric like this. Okay, all right, is this idea making sense? Let's do this again, but in 2 dimensions on this breast cancer classification given these 2 features. So we have these 2 features, and we already saw this plot. We noticed that the benign samples are kind of clustered down in this corner, whereas the malignant samples are kind of spread. So here we have another asymmetric data, right? Like from one class, it's widely distributed, and for the other class, it's kind of tight. And we said that a good boundary should be about down there. But when we train it based on least squares, you can see it pulls the boundary to the right. Instead of being down here, it pulls it over there. And then even on all these red points, which are, we know from the training data they are malignant, this trained classifier is going to report them as benign. So obviously, something is just not working. Okay, so this is just an illustration of this failing in a couple different examples, but kind of in the same way. Okay, any questions on this failure of least squares training? Okay, or failure of the RSS loss. Okay, that's the problem. But I wanted to point out one other thing. There might be a little bit of a mystery as how you go from this equation, the set of x, such that the score z equals 0, to like actually plotting a boundary on a graph. Like if I gave you a really simple, if I told you what b and w were, like could you draw this? So the key is just to rearrange this expression so that it's more convenient to make the plot. So again, like in this case, because we're working with two-dimensional data, this is going to be x1, x2 transpose times w1, w2, right? And that equals x1, w1 plus x2, w2. So what I can now do is I can rearrange things in this equation. So b plus this equals 0. I can move the x2 to the left side, move everything else to the right side, divide everything by w2, and then, make sure I get this expression right. This is what we get. We get minus b over w2 minus w1 over w2 x1. Right, so all I did is simple algebra, rearranging this equation so that x2 appears on the left, x1 appears on the right. And if I give you this equation, this is kind of like a high school plotting exercise, right? You can see that the slope of x2 versus x1 is determined by this number, and that the intercept is this number. Okay, so now that means if on a test, I gave you a simple example like this, and I told you this is what b and w1 and w2 are, draw me the decision boundary in the feature space, you could do that. Okay, all right, so that's another thing we learn on this page. Okay, any questions? Okay, great. Okay, so we now know that something that doesn't work, so what does work? Okay, so just to review, linear classification is a two-stage procedure. Given feature x, weights b and w, we first compute the score z, and then we threshold that score to give us y hat. And our whole goal now is compute those parameters, and minimizing RSS is not a good idea. So what we're going to do is we're going to take our more recent sort of probabilistic view of machine learning, and we will model the true label, which we call y, as a z-dependent random variable. And now this is a discrete random variable, right? It can only take the values 1 and 1. So that means probabilistically, there's just kind of one or two probabilities. There's a probability that y equals 1, and then there's a probability that y equals minus 1, right? And those two things have to add to 1. So you could almost say there's just one probability, this, and then the other one is 1 minus that. Or you can say there's 2 and they have to add to 1. And so what we're saying is let's come up with a model that says what is this probability as a function of z? Z being the score, and y being the true label. So there's many different ways to do this, but there's one that is by far the most popular, and it is based on this equation. So the probability of y equals 1 given z is e to the power z over 1 plus e to the power z. And then the other one is 1 minus that, which we can write as 1 over 1 plus e to the z. Okay, and if we want to visualize this guy, it is actually this down here. So this is z. Sorry, this is x. No, this is z. And this is the probability that y equals 1 given z. Okay. So actually, if you think about it, this is really not that different than what we did in regression, except in regression, we always said, y equals this plus epsilon, where epsilon is Gaussian noise, right? So even there we had a probabilistic model. If we think about this as z, in that case, or I'll write before, we had a density py given z was Gaussian in the variable y with z as the mean and sigma squared as the variance. So all we're doing now is we're changing up our probabilistic model to something that works with this discrete y, whereas this is a continuous y, so this is a PDF. We don't have PDFs anymore because we're working in this discrete space. So we just have a PMF, probability mass function, and it's really just a vector of two probabilities, this one and this one. Okay, so that's what we're doing. We're taking the same approach basically, but we're just changing the details. Okay, so what we're saying is that the larger z is, the more sure I am that their true label equals 1. So you can see as z gets larger, my belief that y equals 1 gets larger and larger. It approaches 1. It will get to 1 as z goes to infinity. On the other hand, for negative z's, if they're large and negative, then I'm almost sure that y is not 1. The probability y equals 1 is very close to 0, and it goes to 0 as z goes to minus infinity. And right in the boundary, when z equals 0, I have absolutely no idea what y is. With probability 1/2, it could be 1. With probability 1/2, it could be minus 1. That's really my point of most uncertainty. Okay. So this is the probabilistic model that is the default or most popular thing that is used for binary classification, especially binary linear classification. Is that kind of making sense at a high level? So we're using probability just as like we did in the last unit to explain the maximum likelihood view of least squares linear regression. It all starts from that probabilistic model, and now we just have a different one. Okay, any questions on this? Very, very important point, obviously. Yes?
Just to clarify, you said the horizontal axis is z.
Yes, exactly. So, right, this is sort of the model. On the next page, I'll translate it to x, but for now, we're just saying, like, if you tell me what z is, then that directly affects my belief on y, right? Yeah. Okay, so another way that we can write this, that is very, very commonly rewritten, is to multiply top and bottom by e to the minus z, in which case you get 1 over 1 plus e to the minus z. Okay, so these are equal, but just two different ways to write it, and I just wanted to point that out. So if you write it this way, you can notice it has a lot of similarity to this, except that the sign of z is changed. And this curve is known as the logistic function or the sigmoidal curve. Okay, great. Okay, any questions on this? Okay, good. And so as the last question suggested, it's like a little weird to be plotting or thinking in terms of z, because z is sort of like this intermediate variable. The question might really be like, well, actually, how does this probability change as a function of x, my feature? Right? That's going to be affected by b and w. So let's see how that works. How does probability of y equals 1 given x behave? So let's take this in two steps. First, let's simplify as much as possible. So we'll just imagine that the feature is a single one, scalar, and let's assume that the intercept for now is b equals 0. So in this case, this is our probabilistic model here, but now z is simply going to be w, our single weight, times x, our single feature, right? So that thing, that z gets plugged into there. So you can think of this as 1 over 1 plus e to the power minus wx, if you like. And here's several plots of that probability y equals 1, plotted now as a function of x, which is maybe, more insightful. And this is plotted for different values of the weight. So if the weight is 1, this is exactly the curve from the previous page. Now, if the weight is 0.5, and notice that these are all on the same, they all use the same exact scaling of the x-axis. So if you shrink the weight, the sigmoidal curve becomes less, the transition is slower. If I increase the weight up to 10, the transition is much faster. It transitions from 0 to 1 almost instantaneously, it looks like. And finally, if we negate the sign on W, it flips. It goes from high to low instead of low to high. Okay, so now you can see the effect of W on its own when we think about this probability of y equals 1 given x. So by changing the weight, we can change how quickly we transition in the x space. Like if I want to have a really sharp boundary, if I want to say like samples on this side of the boundary are very confidently -1 and samples over here are very confidently 1, then I want to use a large W. But if I have a lot of samples on the boundary and it's not really clear around at the boundary, what class I should use, then I would want something soft, which corresponds to a smaller W. Okay. Good. Any questions on that? Is that making sense? All right, so now let's bring in, and this is all for b equals 0. And so in this case, when b equals 0, the transition, where the probability is 0.5, this always occurs at the origin of x. Okay, so it's always centered at x equals 0. So now let's consider what happens if b is a general real number. So in this case, we know that z equals b plus wx. It actually helps to rewrite this a little bit as w times the quantity b over w plus x. And now the reason we write it this way is that we can see how b and w just translate these curves in the x domain. So basically the transition, instead of being at 0, the transition is now going to be, let me see, is Yingzhe Zhang here? Yeah. So what do you think the transition is going to be at, what x does it go to? So I want an equation here. So rather than the transition centering at x equals 0, now it's centered where? Exactly. Minus b over w. Okay, so now you can see that the effect of b in our model is to shift the location of the transition, but it also affects the steepness too. W also, W and B together affect the transition. Great, okay. So is this making a little bit more sense, like what's happening with this? Okay, great. So now, how exactly are we going to do the fitting? Well, we're going to use this tool, maximum likelihood estimation, which I said is going to be the main tool we use for the remainder of the term. And just to quickly review what ML estimation is, the first thing is, number one, step one, we define some likelihood function, which is going to be the probability or the probability density of y, the vector of training samples, given a matrix of training features and our trainable parameters. We have previously called those theta. And that's step one. And once we know that model, we just find for fixed data, training data, fixed training data, sorry, very sloppy writing. Fixed training data, y and x, we figure out the b and the w to maximize this likelihood. And we said that often in practice, the expressions get a lot simplified if we take the negative log of the likelihood, so we can equivalently minimize the negative log likelihood. So that's the general procedure. And then we did this for linear regression. And for that, we used this likelihood, which I alluded to on the previous page, So here we have a Gaussian model where the mean is alpha times beta and the variance is sigma squared. And when you plug this in, when you take the negative log of this, you get this expression, which is a quadratic plus a constant. And then the minimizer of this with respect to beta is the same thing as minimizing RSS. Okay, so that's just a review of what we did in the last lecture. And we're just repeating this procedure, turning the crank again, but with a different likelihood function, the one we just defined based on the logistic. Okay, so this is our plan. Use maximum likelihood, but with this model over here. Okay, any questions on this? It's kind of making sense? Okay, so let's see the details then. Okay, so our model, we actually have to write it with two equations because there's no single equation that describes our model. So our model, in the case that the ith target equals 1, this probability is e to the power zi over 1 plus e to the power zi. And remember, zi now is a function of the training features for that sample as well as our tunable parameters, b and w. So this is what happens if y equals 1. But then if y equals minus 1, or the probability that y equals minus 1, we actually have a different expression that, it's just fundamentally different. So, so what we do is we have to use a little trick in our derivation, which I'll get to in a moment. But anyway, the flow of the derivation is the same thing we will see in every maximum likelihood problem. So we start with our likelihood, and we have always and will always assume independence among our training samples, which means that this joint probability density can be written as a product of scalar or marginal densities, one for each training sample. And so that means that the negative log of the joint gives us the negative sum of the logs of these marginals because of this log identity. Log of quantity CD is log of C plus log of D. So that basically with this turns this product into a sum of logs. Okay, so here we are with the sum of logs, and now this is where we have to apply this trick. So I know that this takes on one of these two expressions depending on the value of yi. So the trick we're going to use is based on what I call some switching variables. And here are my switching variables that I'm going to insert. One way to think about it is that I have put in this number minus the same thing, which canceled to 0. Another way to think about it is, okay, this number, I kind of carefully constructed this little fraction so that because y is 1 or minus 1, this fraction equals either 1 or 0. So it equals 1 whenever the sample's yi equals 1, 0 otherwise. And then this one is like the counterpart. This one, when this one equals 1, this one equals minus 1 and vice versa. Okay, so now that means that whenever yi equals minus 1, this thing goes to 0, and that means that I can plug in for this the expression that holds when yi equals 1. I don't have to worry about this other case because in this other case, this term drops out. So therefore, when yi equals 1, that's going to give me the first term here, and then when yi equals minus 1, I'm going to plug that in for the second term. Okay, so basically these switching variables switch on or off, allowing me to plug in for these the one of the two expressions we have above. Is that making sense? That's really the difficult thing about this derivation. It's just that little trick. Everything else is just very straightforward algebra. Okay, any questions on the trick? Okay, so now we just have to do a little bit of algebra. So let's focus on the case of y equals 1, which is this expression. I need to take the log of that. So I'm going to get log of numerator, which is zi, minus log of the denominator, which is this. And there's really no way to simplify that term. So that's just what we have. So that's what this gives us. The log of that is this. And then we need to take the log of this. And so log of numerator is 0, and then minus log of the denominator is this other term. Okay. So when we take the log, basically log, we get this expression. Okay. Now, fortunately, so the next thing is we just expand out the terms. So we have this times this is the first term, this times this is the second term, this times 0, don't need to include that, so then we have this times this as the third term over here. And fortunately, a couple of these cancel out, so this one cancels this one. And so we are left with these two terms. And this really can't be simplified anymore. So this is our negative log likelihood, the thing which we want to minimize to obtain our parameters b and vector w. So this is what we need to do. Now, unfortunately, this is not something that you can derive on paper, like in this linear Gaussian case that we talked about here. We actually were able to derive the least squares solution, and it gave us this like matrix equation with an inverse. There's no such thing anymore for this. So this is something that we need to do with an algorithm on a computer. But once again, this is a convex optimization, and it can be done. And there's algorithms to do it, and they're programmed in sklearn. We'll come back to this in Unit 6 to understand more about how those algorithms work. But for now, we can just say someone has solved that problem. So now let's go back to our simple data set. This is the one-dimensional case. This is least squares linear. This is the plot we saw before, where we move this point out, and consequently, we saw that the trained regressor is making a mistake on that data sample. But now with logistic regression, we minimize this thing in software, and we take the computed parameters and we plug them in. And so this is what we have for the line for our new z-hat. You can see that it's steeper and it's centered at the right spot. When we threshold that line, we get these hard decisions, which are perfect, very symmetric, even though our data is not symmetric. And we're also able to plot the probability that y equals 1 given x according to our model. And so we can see that, as our x get far beyond 5, we're more and more confident that the label is 1. But when they're close to the boundary, we're not really that confident about the data based on the least squares fit we did. Okay, so this is what we have for this example, and I realize I've gone a couple of minutes over, so I apologize for that. So this is all we have for today. If you have any questions, just ask me after class. See you guys on Friday.